Good day, I'm Marimar, and I'm going to teach you about two-way ANOVA or analysis of variance. What is two-way ANOVA? Say, two-way ANOVA is a statistical test that determines how two independent variables affect a dependent variable. It is used to understand if there's an action between the independent variables and to estimate how the mean of the quantitative variable changes based on the levels of categorical variable. It is also used to estimate how the meaning of quantitative variable changes according to the levels of two categorical variables. Use of two-way ANOVA when you want to know how two independent variables in combination affect a dependent variable. There is a quantitative variable that represents the amount or types of things it can be divided to find a group of mean. While the categorical variable represents types of categories of things. A level is an individual category within the categorical variable. So the two-way ANOVA test a null hypothesis at the same time. First null hypothesis is that there is no difference in group means at any level of the first independent variable. Second is there is no significant difference in group means at any level of the second independent variable. And third is the effect of the independent variable does not depend on the effect of the other independent variable, or there is no interaction. There are assumptions of two-way ANOVA. To use two-way ANOVA, your data should meet certain assumptions. Two-way ANOVA makes all the normal assumptions of a parametric test difference. Number one is homogeneity of variance, or aka homozydicity. The variation of the mean for each group being compared should be similar among all groups. If your data don't meet this assumption, you may be able to use non-parametric alternative like Ruskal values test. Number two, independence observation. Your independent variables should not be dependent on one another. One should not cause the other. This is impossible to test with categorical variables. It can only be ensured by good experimental design. In addition, your dependent variable should represent unique observations. That is, your observation should not be true within locations or individuals. If your data don't meet this assumption, you can include a blocking variable and use a repeated measures of ANOVA. And third, normally distributed dependent variable. The values of dependent variable should follow a bell curve. They should be normally distributed. If your data don't meet this assumption, you can try a data transformation. Remember, when you do a two-way ANOVA, we need to assume that our data is normally distributed and that the population standard deviations are equal. Therefore, we must make sure that twice our sample standard deviation is larger than our largest standard deviation. There are advantages in using two-way ANOVA. It is more efficient to study two factors simultaneously rather than separately. We can reduce residual variation a model by including a second factor to the group of influence the respondents, and we can investigate interactions between factors. Here is a table for two-way ANOVA, which is important in conducting the test statistics, which will be further discussed to the next slides. Like other test statistics, two-way ANOVA also uses the F table for F table critical value for 0.05, 0.10, and 0.01. Although usually statisticians on into ANOVA it is 0.5 is usually used. So ANOVA equals variance between over variance within, and total ANOVA is variance between plus variance within. For decision making, if the computed f is greater than the p-value, then we should reject the null hypothesis. And if the f computed is less than or equal to p-value, then we should accept the null hypothesis or retain it. So here is a sample problem. A research study was conducted to examine the impact of eating a high-protein breakfast on adolescents' performance during a physical fitness test. Some of the subjects received the high-protein breakfast, some were given a low-protein breakfast, and some were given no protein at all. All of the adolescents, both male and female, were given a fitness test with high scores representing their better performance. Test scores are recorded below. Test at 5% level of significance. So here are the data that is gathered from the fitness test. First thing to do is define the null and alternative hypothesis. So our null hypothesis is that there is no impact of eating high protein breakfast on adolescents' performance during the physical education fitness test. Second is there is no significant difference between protein content, and there was no interaction between protein breakfast and physical education fitness test. Step 2 is the null hypothesis, which in this case will be using 0.05. And then the next step is to calculate the degrees of freedom. To calculate the degrees of freedom for protein, you should be using column minus C minus 1, or C stands for column, R minus 1, R stands for row, C minus 1 times R minus 1, C times R times N minus 1, and total is N minus 1. In this slide, you can see how the DF are calculated. For the DF gender, C minus 1. For the protein, R minus 1. For the interaction, C minus 1 times R minus 1. And for the DF error or the residual, N minus R is C. And for the total, N minus 1. You put the results in the table so you can navigate or track the results. Step 4 is the state decision rule. For gender, DF gender times DF error, CV, the critical value here is 4.17. So if f is greater than 4.17, we reject the null hypothesis. For the protein, the critical value is 3.32, which means if the f is greater than 3.32, we reject the null hypothesis. And for the interaction, the CV is 3.32. So if the f is greater than 3.32, we reject the null hypothesis. Then proceed to step 5. Step 5 is to calculate the statistics by getting the sum of squares. First, we get the sum of squares of gender using the equation summation of A squared over bn minus r squared over n. So you get the sum of the height of all the males, high protein, low protein, and no protein, which is 687, and for the female is 59. You square both divided by 3, the number of columns, and 6 because there are 6 6 sets of data for both male. For male, there is 3. For female, there is another 3. Minus 146, the total of all this data over squared over 36. Then we get the gender. Then we continue to solve. Then we will come up with 21.76. Next is to calculate the sum of squares of protein. Same procedure but different data because here you will be using the the pro the sum of the columns unlike before the rows, and the low protein, the high protein, the number of protein, sum them all up, and you divide it by 2 times 6. 2 because there are 2 rows, and 6 because there are 6 sets of data. minus 146 squared over 36. Then you come up with 32.72. Next is to calculate the sum of squares of the interaction. The red the red numbers represent the total of each of the columns. So you'll be using that. And then you proceed. You'll also be using the total for the sum of squares of gender and protein. Then the sum of squares of interaction minus the sum of squares of protein minus the sum of squares of gender plus p squared over n, which is um the total, of course. Next, then we get the total of the y minus r squared over n. So the sum of squares of the total is 764 minus 146 squared over 36, then you come up with 171.89. Here are the tally of the scores. You're just going to track it in that table so you will it will be easy for you. Then you get the mean of the squares. Here it's easy because you just follow this. You just follow the formula written. Its mean of sum of squares is equals to the sum of squares over their respective df. So here you just 21.78 divided by 1, you get 21.78. 32.72 divided by 2, you get 16.36. So on until you get the total. Here are the um here are to calculate the mean of squares. You may pause to further to understand it better. And then you will be using and then lastly you will be getting the F ratio or the F. F is computed by using the mean of squares over the mean of squares of the gender, protein, and the interaction over the mean of squares of standard error or the residual. So the 6.72 is get by dividing 21.78 over 3.24. As you can see here, you got 6.72. Then 16 for the protein, 16.36 divided by 3.24, 5.05. And then for the interaction, 10.03 divided by 3.24 is 3.10. So step 6, you state the rules. If f before we discussed the decision rule, so here it is. F is equals to 6.72, so we reject the HO. F is equals to 5.05, so we reject the HO. And F is equals to 3.05, so we accept the HO. And then you take the conclusion. The conclusion is that there is an impact of eating high protein breakfast on adolescents' performance during a physical education fitness test. F130, this is the DF where you got the difference from the DF table equals 6.72. P is greater than 0.05. There was also a significant difference between protein content. F230 equals 5.05. P value is greater than 0.05. But there was no interaction. F230 equals 3.10. P is less than 0.05. Thank you, and that's